Welcome to this model. Today we are going to see about IPv6 addressing. The network layer protocol in the TCP/IP protocol suite is currently IPv4, that is version 4, Internet Working Protocol version 4, which provides the host-to-host communication between systems in the Internet. Although IPv4 is well designed, data communication has evolved since the inception of IPv4 in 1970s. IPv4 has some deficiencies that make it unsuitable for the fast-growing internet. Let's see first the disadvantages of IPv4. Despite all short-term solutions such as subnetting, classless addressing, and NAT, address depletion is still a long-term problem in the internet. The internet must accommodate real-time audio and video transmission. This type of transmission requires minimum delay strategies and reservation of resources not provided in the IPv4 design. The internet must accommodate encryption and authentication of data for some applications. No encryption or authentication is provided by IPv4. So to overcome these deficiencies, IPv6, Internet Networking Protocol version 6, also known as IPNG, that is Internet Networking Protocol Next Generation, was proposed and is now a standard. In IPv6, the Internet Protocol was extensively modified to accommodate the unforeseen growth of the Internet. The format and the length of the IP address were changed along with the packet format. Related protocols such as ICMP were also modified. Other protocols in the network layer such as ARP, RARP and IGMP were either deleted or included in ICMP version 6 protocol. Routing protocols such as RIP and OSPF are also slightly modified to accommodate these changes. Communication experts predict the IPv6 and its related protocol will soon replace the current IP version. So now in this model, let us discuss about IPv6. Then we explore the strategies used for the transition from version 4 to version 6. Now the adoption of IPv6 has been slow. The reason is that the original motivation for its development, depletion of IPv4 addresses, has been remedied by short-term strategies such as classless addressing and NAT. However, the fast-spreading use of the internet and new services such as mobile IP, IP telephony and IP-capable mobile telephony may eventually require a total replacement of IPv4 with IPv6. The main reason for migration from IPv4 to IPv6 is the small size of address space in IPv4. And the next generation IP, that is IPv6, has some advantages over IPv4 that we can summarize now. The first case is large address space. The IPv address is 128 bits long. So compared to with 32-bit address of IPv4, this is huge. That is 2 power 96 increase in the address space. And it has better header format. IPv6 uses a new header format in which the options are separated by the base header and inserted whenever needed between the base header and the upper layer data, right? This simplifies and speeds up the routing process because most of the options do not need to be checked by the routers. IPv6 has new options to allow for additional functionalities. IPv6 is designed to allow the extension of protocol if required by new technologies or applications. In IPv6, the type of service field has been removed, but a mechanism has been added to enable the source to request special handling of the packet. This mechanism can be used to support traffic such as real-time audio and video. The encryption and authentication options in IPv6 provide confidentiality and integrity of the packet. Each packet is composed of a mandatory base header followed by the payload. The payload consists of two parts, that is optional extension headers and the data from an upper layer. The base header occupies 40 bytes, whereas the extension headers and data from the upper layer contains up to 65,535 bytes of information. Now let's see the base header informations. The base header has 8 fields. The version field is a 4-bit field which defines the version number of IP. For IPv6, the value is 6 now. And the priority, 4-bit priority field defines the priority of the packet with respect to traffic congestion. And flow field, the flow field is a 3-byte, that is 24-bit field, is designed to provide special handling for a particular flow data. The 2-byte payload length defines the length of the IP datagram excluding the base header. The next header is an 8-bit field defining the header that follow the base header in the datagram. The next header is either one of the optional extension headers used by the IP or the header of an encapsulated packet such as UDP or TCP. Each extension header also contains this field, and the 8-bit hop field serves the same purpose as the TTL field in IPv4. The source address field is a 16-byte, that is 128-bit internal address that identifies the original source of the datagram. And the destination address field is a 16-byte 128-bit internet address that usually identifies the final destination of the datagram. However, if source routing is used, this field contains the address of the next router. Although the IPv6 address, even in hexadecimal format, is very long, many of the digits are zeros. So in this case, we can abbreviate the address. The leading zeros section can be omitted. Using this form, abbreviation 0074 can be written as only 74. You can omit 00. And 00F as only F and 000 as 0. You can note that 3210 cannot be abbreviated. Further abbreviations, often called the zero compression, can be applied to the colon hex notation if there are connective sections consisting of zeros only. So we can remove all the zeros and replace them with a double semicolon. So this example shows how we remove all the zeros and only double semicolon here, right? So this type of abbreviation is allowed only once per address. If there is more than one run of zero sections, only one of them can be compressed, the remaining cannot be compressed. And the priority field of IPv6 packet defines the priority of each packet with respect to other packets from the same source. For example, if one of two consecutive datagrams must be discarded due to congestion, the datagram with the lower packet priority will be discarded. IPv6 divides the traffic into two broad categories: congestion controlled and non-congestion controlled. If a source adapts itself to traffic slowdown when there is congestion, the traffic is referred to as congestion controlled traffic. For example, TCP, which uses the sliding window protocol, can easily respond to traffic. In congestion controlled traffic, it is understood that packets may be arrived delayed, lost, or out of order. Congestion control data are assigned priorities from 0 to 7. So 0 means no specific traffic, 1 means background data, 2 unattended data traffic, 3 reserved, and 4 is attended bulk data traffic, 5 reserved, and 6 interactive traffic, and 7 is control traffic. And a priority 0 is assigned to a packet when the process doesn't define a priority. And this group, background data group, that is priority 1, defines data that are usually delivered in the background. Delivery of the news is a good example. And an unattended data traffic means if a user is not waiting for the data to be received, the packet will be given a priority of 2. Email belongs to this group only because the receiver will not wait for the data to come. Whenever he opens a mail, he can receive the data now. So the recipient of the email doesn't know when a message has arrived. In addition, the email is usually stored before it is forwarded. A little bit of delay is of little consequence. And a protocol that transfers data while the user is waiting to receive data is given a priority of 4. FTP and HTTP belong to this group. Protocols such as Telnet that need user interaction are assigned the second highest priority 6 in this group. And control traffic is given the highest priority 7. Routing protocols such as OSPF, RIP, and management protocols such as SNMP have this priority. And non-congestion controlled traffic refers to a type of traffic that expects a minimum delay. Discarding of packet is not desirable here. Retransmission in most cases is impossible. In other words, the source doesn't adapt itself to congestion. Real-time audio and video are examples of this type of traffic. Priority numbers 8 to 15 are assigned to non-congestion control traffic. Although there are not yet any particular standard assignments for this type of data, the priorities are usually based on how much the quality of the received data is affected by discarding the packets. Data containing less redundancy can be given highest priority 15, and data containing more redundancy are given the lowest priority, that is 8. And a sequence of packets sent from a particular source to a particular destination that needs special handling by routers is called flow of packets. The combination of the source and source address and the value of the flow label uniquely defines flow of packets. So to a router, flow is a sequence of packets that share the same characteristics such as the traveling the same path, using the same resources, having the same kind of security, and so on. A router that supports the handling of flow labels has a flow label table. So the tables has an entry for each active flow table, and each entry defines the service required by the corresponding flow label. And the router receives a packet, it consults its flow label table to find the corresponding entry for the flow label value defined in the packet. It then provides the packet with the services mentioned in the entry, and you can notice that the flow label itself doesn't provide the information for the entries of the flow label table, and the information is provided by other means such as hop by hop options or other protocols. Thank you.